for 1 minute so that people. Usually it is all exactly 4 o'clock. So just wait for 1 minute. Let Thangavalu sir introduce Rani. Then.
Oh, you can introduce her. Kalachand can.
No,
No need
no,
of me.
no. It is
You can
good that you
introduce her.
should really. So whenever people hear your voice, they become happy and excited.
What?
Yeah. Yeah, sir, you can start.
We can start, right?
Yes.
Yeah.
Kalachan, yeah, start.
Yeah. Oh,
What happened?
something when I think
Yeah,
I love what
IIC.
happened to
I think
what
IIC
happened to
website.
oh
Something wrong with IIC internet.
yeah. Yeah.
No, I
Maybe
can see it actually. I can
I
see
don't know
Rani's slide.
no what happened. Something happened to my connection maybe.
Yeah.
Anyway, we can start now. I think we are happy to have. No, there is an echo.
So you have logged in from 2 accounts, I think. It is showing 2 accounts.
Oh.
One is your name, another is Beluma. So
No. Wait. I don't know what. Something wrong. No, why don't you join? Why don't you start? I will join.
Sure, sir. Okay.
Okay, just wait. So welcome to this APRG seminar. It is my pleasure to introduce today's speaker, Senthil Raani from IISER Berhampur. The title of her talk is Large Distances in Sets of Positive Density. Okay, so and with this, I would like to invite her to deliver the talk, and I also request all the participants to mute their microphone. Over to you, Senthil.
Thank you, Munna. Thank you for the invitation. I'm going to talk about large distances and sets of positive density in two setup. One is Euclidean setup and Heisenberg group setup. So, okay, so the outline of the talk is going to be a very brief history on this particular problem that I'm going to state. And then we will go ahead with the original statement of Bourgain, who gave the Szemerédi-type theorem, which basically addresses like when do we have large distances in a given set of positive density. And we will see a brief example given by Alex Rice to see the optimality of Bourgain's theorem. And then we will go through the techniques of Bourgain's proof, and we run parallelly how Bourgain's proof can be mirrored for Heisenberg group setup. Okay, so what do we mean by positive upper density? So for any discrete set to begin with, if we have a subset of integers, the positive upper density is defined to be the cardinality of the set intersected with a set of all n natural numbers with the quotient to n. So when as n tends to infinity, we try to see if it is positive, and we call this as upper density. The easiest example that one can see is twice the set of natural number, which will have density to be half. And say, for example, collection of all 10 divisible natural number, that density will be of 9 by 10. So I think you will be able to see the pattern clearly to figure out how the density is measured. Once we have a positive upper density, it is kind of trivial that like we will have distances. In other words, what do I mean by distances? Like I can definitely find 2 points in the integers such that a and a plus d will be inside a. And Roth also in 53 and 72, consequently, they observed that a admits of the sets of the form 3 configurations and 4 configurations as well. Finally, in 1975, Szemerédi proved that like whenever we have positive apparentity, all large K-term progressions is going to be inside that set. So this is the start of our topic. So this is in the discrete setup, and of course this was proved via combinatorics method, and later by Gowers, like we had the proof in Fourier analytic approach, but I'm yet to read the Fourier analytic approach for this particular theorem. Anyway, this discrete setup is quite interesting to itself, and our goal is to see what happens if we are going to go for a continuum setup. Okay, so if I'm going to start with any subset in R or Rn for that matter, then we are talking about density, which is now going to be replacing the cardinality by the measure that we have in Rn. So technically here mod of A intersection B of 0, R is going to be n-dimensional Lebesgue measure of that set. So if it is going to behave really well like R to the power n, then we call the upper density to be positive. And our question now is, can I find two real numbers such that, sorry, if I'm giving you x belonging to A, and if I'm going to translate it with respect to a real number L, then will I have x and x plus L to be inside A? If it is real number, like we are in, I mean, if we are in R, then we are talking about real numbers here. And if we are in Rn, we are going to talk about, say, x plus L omega. Now, in other words, this can be restated that like you give me a real number, then the distance between 2 points, can I find 2 points in that set such that the distance between 2 points is going to be L? So in general, when I'm going to say for every positive real number, will A be admitting this distance? We are technically asking that the distance set itself is going to be the complete set, which is 0, infinity. So these are the questions that one can ask to begin with before going for, like a larger term progressions or a different kind of a pattern. So the intuition, at least from the discrete set, says that, okay, definitely if you have positive density, I'll definitely be able to say sufficiently large distances. What do we mean by that? Like after a point, every large distance is going to be inside the distance set. So with this intuition, we are wrapping up the history. So in 1970, Bodeman, and in 1999, Siegfried and Ladislav had figured out like what are the sets of positive upper density that admit all distances, which is true or not. And Bourgain answered that question positively whenever for a set to be admitting sufficiently large distances. While the proof in Bourgain's paper is only planar, it's also given, the proof follows for n greater than or equal to 2. N equal to 1 is still open, and it is also in pipeline of another project.
So this Bourgain's result says that admits all sufficiently large distance or some particular.
Admits all sufficiently large distances, not all large distances. Like all distances means that this is going to be equal 0, infinity. But what we are currently saying is sufficiently all large distances, which means there exists an L such that L, infinity is going to be sitting inside delta of A. So Bourgain had proved this.
Okay.
And so the hypothesis is basically sets of positive upper density. So Bourgain, whether the hypothesis is strong enough or not was addressed by Rice. And the techniques were we kind of refined the techniques with Pramanik. And finally, the Heisenberg group setup, what will be the mirror statement of all of these results is what, was a work with Rajesh, which has been recently submitted. So in this talk, what I'm going to do is that I'm going to focus on 3 topics. So since the examples that were discussed in Bodeman and 1999 paper are quite easy to see, I'm leaving it to the audience for whoever is interested in. And since the proof of Bourgain's, the proof and his techniques were actually applicable for Rn for n greater than or equal to 2, we are going to give a brief revision of all these techniques in Rn generally for n greater than or equal to 2. And finally, we will finish up with the Heisenberg group setup. So now we will start with what do you mean by sharp, whether the result of Bourgain is sharp or not. So Bourgain's result says that positive upper density gives you sufficiently all large distances. However, Rice proved that if I'm going to start with a slowly decaying density, it means to say that if I'm starting with the Lebesgue measure of the set intersected with a ball of radius Rm is going to kind of like slowly, decay as like whatever the decay that you're going to give, but it has to be slow decay. Then we will be able to say that it doesn't admit all sufficiently large distance, which means whatever the Rm that you're going to give, there will be no X and Y's in A such that their distance will be in Rm. And the construction of this set that Rice gave was quite simple. You have the sequence Rm, like you start with an arbitrary sequence Rm. With respect to the sequence of Rm, you are going to construct a very small radius, say epsilon m's, and you're going to carefully place at each level or a ball of radius epsilon m at every Rm distance from the previous level of Rm minus 1 distance. So as you carefully place these balls in a particular manner, you'll be able to say that it avoids all distances Rm. Now, the proof that was given by Alex Rice was actually applicable for most of the metric spaces. And hence, in Heisenberg group setup as well, this statement analogously hold. So here, instead of n-dimensional Lebesgue measure, we will go for hard measure. Instead of the translation group action, instead of the plus group action in Euclidean setup, we will go for the original group action that is available in Heisenberg group setup. So I'm leaving the slide at this because we are not going further because it's kind of like an easy observation. Okay, so now let's start with the Euclidean setup. So here I'm going to go a bit slow in the Euclidean setup because I'm going to draw analog of what is going on Euclidean setup and what will be going on in Heisenberg group setup. And the final goal.
Sorry, you said that Bourgain's result is for planar region, right?
Yes.
But this result is about dimension n, right? This Bourgain.
So n greater than or equal to 2. So Bourgain had given the proof for n equal to 2. However, his proof follows for n greater than or equal to 2.
Okay, so this is a general result. Okay.
This is a general result. Of course, but n greater than or equal to 2, n equal to 1, it's not proved. This technique fails for n equal to 1.
Oh, okay. So this result is still open for n is equal to 1?
So currently we are trying that in different, for Euclidean setup, we are currently trying it and we're trying it with Ashwin.
Okay.
For n equal to 1.
I had a quick question, if I can ask, for n equal to 1.
Yes, please.
So I don't, maybe I'm missing something very clearly, but if you just take somehow the set, let's say, take 0, 1/3, union 1, 4/3, union 2, 7/3, like just the first 1/3 of 18. Then set up the density, sorry.
Sorry, we are considering infinite union in the 1/3 of interval, is it?
1/3 of every interval, infinite union, yes.
So every 1/3 of every interval, right?
The first 1/3 of every unit interval, yes. That is,
yeah, okay. Correct. So n equal to 1, it fails. When I said like what we are working is like if we can actually figure out an additional hypothesis, because with Malabika, that's what we try to do. Like we kind of like saw what are the additional hypotheses that we can say for even, slow decaying sets where not satisfying all sufficiently large distances, but like say Hausdorff measure being positive was giving us some sufficiently all large distances. So in that sense,
all sufficiently large. This is not like excluding some null set or anything like that. You want
no, that's yes, sufficiently all large distances, yes.
Okay, thank you.
Yeah. So for n equal to 1, we are still trying. So we don't have a result yet, but we have quite a few observations, but it's still on pipeline.
So when you say what is open is you're saying it's open, what is some extra sufficient condition to ensure?
Correct. Right. Okay. So okay, now let's go to Bourgain's techniques. So this is the statement of Bourgain's theorem, and let's see how to prove this. So the first and foremost step to address this problem is to reduce to a quantitative statement. So first, let's see what happens by contradiction. If we are not able to prove that, then we are saying that like there will be a sequence of points, distances that are avoided by A, which means there exist L1, L2, which are very large such that it will not have any distances. And the density will still be greater than 0. Let's say it is delta. So with some parameter adjustment, like if I can actually shrink this whole set A with appropriate dilation, say 1 over R, and consider that set to be inside B of 0, 1. So in this kind of dilated sets, because we are saying that the LJs are avoided by A, then the corresponding dilates will also be avoided in E. In other words, TJs are not going to be distances in E. And if I'm going to say that, give a contradiction to this, then we are done. So what do I mean by that? If I'm able to say that at least one J, the collection of all x comma omega will be having a positive measure, then we arrive at a contradiction. So technically, it's good enough to say if I'm going to consider this configuration integral, and if I'm able to say at least for one J, this configuration integral is going to be positive, then we are done with the proof. So altogether, these two slides combined with, we can actually restate it into a reduced quantitative statement that with an appropriate parameter that is arising from the lim sup and the given hypothesis. If I'm able to give you a lacunary sequence TJs which are behaving in this fashion, then I'll be able to find at least one J such that for that TJ, the configuration integral that we talked about is greater than or equal to epsilon square. So it boils down to proving this. Now, we can see that here as well, there is no much of analysis. It's mostly how the group has been behaving. Okay, so now finally to prove the reduced statement, once we have the reduction, how do we prove it back in Euclidean setup? Is that we first use the Fourier inversion to kind of write it in terms of the frequency space instead of the original space. So I'm going to write integral Fourier transform of characteristic function E mod squared sigma hat of Tj zeta, where sigma is my surface measure, unit surface, normalized surface measure on Sn minus 1. And the second step that Bourgain does is split this integral into 3 different frequency domains. Whenever mod zeta is small with respect to Tj inverse, and whenever it is between delta and delta inverse, and then whenever mod zeta is high. So with these 3 frequencies split, like once we split this, now each of the properties that we have in the hypothesis, that sigma being unit normalized surface measure, we will be able to say that the sigma hat can be bounded below by a specific constant that depends only on delta. And further, this can be bounded below by the particular n-dimensional Lebesgue measure of E. Again, using the properties of, again, this is Lebesgue measure of E, and hence we will be able to actually bound this below by E. And we have assumed that like mod E is basically greater than epsilon. Lebesgue measure of E is greater than epsilon. So this doesn't involve anything but unit normalized surface measure and the Fourier transform properties. And then the high frequency, on the other hand, is also easy to see because we have a very explicit property of the Fourier transform of sigma. So because sigma hat has pointwise asymptotic, if we are going to plug in the pointwise asymptotic, I'll be able to say that mod hj is going to be less than or equal to delta to the power n minus 1 times mod e. Again, we are using we are exploiting the nature of E here and the Fourier decay property of sigma. So with an appropriate choice of delta, because the delta is something that we were initially fixing, and hence with an appropriate delta, we will be able to say that hj is also going to be very small than the bounds that we get for Lj. So combining Lj and hj, now the equation becomes that the configuration integral is going to be greater than or equal to epsilon square plus middle frequency. So here the delta is now fixed, and what we have now is MJs, and here is where the lacunary condition on TJ going to play a very vital role. So if we have the lacunary conditions on TJ, with respect to that, we carefully choose the delta such a way that this set is going to overlap only with multiplicity, say order of log delta inverse. You can either say it's not going to overlap with the choice of delta to be in this fashion. So yeah, like generically, what we are trying to do is we are summing it up so that we will be able to use the pigeonhole principle. So once we sum the MJs, so MJ for me was basically this integrand with the middle domain to be this. So if I'm going to sum it over and this overlap is going to be at multiplicity, say order of log delta inverse, then this altogether is going to give me the integral mod of Fourier transform of characteristic function of E. By Plancherel, it is going to be again mod of E. So that is what we have got here. The multiplicity is used to find out the bound, and the Plancherel is giving me mod E here. Now, since summation Mj is going to behave like this by pigeonhole principle, at least one Mj is going to be log delta inverse divided by J, where capital J is the number of Tj's that we had originally assumed. So with respect to that, we have one MJ, which is going to be less than or equal to this. And we had already carefully chosen the epsilons and delta in such a fashion that this is going to be less than epsilon squared. Okay, so this pigeonhole principle finally gives us the middle frequency as well, and hence the Bourgain's proof is completed. Now, let's go for Heisenberg group setup. So for the Heisenberg group setup, like now we have different group laws, and the dilation is given by RZ R square T, and the homogeneous dimension is going to be 2n plus 2. We have Coriani norm. We are going to start with Coriani norm, and with respect to the Coriani norm, we are going to define the distance and balls as well. And here we are going to look at the Haar measure, which is also going to be a 2n plus 1 dimensional Lebesgue measure for us. So with respect to Haar measure, now we define Coriani upper density. So this is the mirror that we were talking about from Euclidean setup to Heisenberg group setup. So once we have all of these set up, now we are ready to state what is the statement that as long as I have Coriani upper density to be positive, then I should be still able to find out all sufficiently large distances. Remember, we had already kind of like a sufficient hypothesis, as in like Rice example was applicable for Coriani setup as well. And hence, this is the best that right now we can assume for the hypothesis in order to say. And another interesting fact to note is this is true for all n greater than or equal to 1 in Heisenberg group setup. Okay, so the first and foremost step, just like Euclidean setup, what we are going to do is that we are going to reduce it. Now, remember in Euclidean setup, like when we actually looked for the reduction, we went by contradiction. You can see that here everything was numerical values and only metric space definitions were used. And the group actions was also not playing a vital role here because we were talking about like left translations over here. So because of the similar pattern that we have in the Euclidean setup, like we can actually say that the same proof goes for Heisenberg group setup as well. And hence the reduced quantitative statement is going to be exactly like Euclidean setup. So you give me a hypothesis similar to the epsilons and the lacunary sequence of Tj that we had it in Euclidean setup. Here I'm writing it as RJs. And then these scales are going to be by pigeonhole principle. We are going to prove again that one RJ is going to satisfy the positive configuration integral, just like in Euclidean setup. Okay, so now the next main question to address is how do we go from here using Fourier transform side? Now, unlike Euclidean setup, now we are actually talking about operators and not talking about functions. So since we have group Fourier transform to be an operator valued function defined via the Schrödinger representation, now we will be writing it in Hilbert-Schmidt's norm if we are going to use Plancherel. So every like technique that we have seen in Euclidean setup is going to be mirrored in a different way. So what do we do? But the pattern is going to be the same, and that is why it's kind of like easy to follow. We are going to write it in the Fourier inversion fashion like we did it in Euclidean setup, but now we will be using the Fourier transform of the surface measure on the Coriani sphere. So sigma hat of lambda being an operator valued function, we will be able to write down in terms of the eigenfunctions of the scaled Hermite operators. And hence, if I'm going to plug it in over there, we will be able to get this configuration integral written in this fashion. So here, the most important factor to be considered is that like the coefficients of the group Fourier transform of surface measure RK lambda is the main, main tool that's going to play heavily in our complete computations, in the whole computations. Okay, so what do I mean by that? The first step in the Euclidean setup after using the Fourier inversion was to divide this integral into 3 frequency domain: lower frequency domain, middle frequency domain, and higher frequency domain. So here as well, we are going to do the same thing, but now the division of this frequency domain is going to be with respect to the eigenvalues. What do I mean by that? So you can see that like here, we are going to split up the sum into lower frequency, higher frequency, and middle frequency. So like this factor of, each of this L middle, I'm sorry, there is missing H here. So the higher frequency, we are going to deal with all of these 3 steps again in a similar fashion. But for everything, we would like to bring in the correct tool. So what are the tools that are required? For the lower frequency, what do we do first is using the Lagarde polynomials asymptotes, like using the Lagarde polynomial asymptotes. The first and foremost thing that we observe is that whenever we have the eigenvalues to be small, we will be able to write RK lambda as an order of mu lambda to the power half. And this asymptotic notation is the first thing that is going to tell you that the lower frequency is going to be bounded below by mod E square. So it's asymptotic, so we will keep this in mind because the asymptotic with respect to the K here is going to be addressed towards the end of the talk. So we will keep going with this asymptotics and we will first see how the whole proof outline goes. So the lower frequency now is attained as long as I'm able to obtain this. But this is going to be very easy. This lemma is easy to prove. It just needs, we just have to incorporate Lagarde polynomials asymptotes. And the next easy part is the mid frequency. Why it is easy is that it's going to be similar to the Euclidean setup. Like the same pigeonhole argument that we did in Euclidean setup is going to be falling hand in Heisenberg group setup as well. The only difference between this and Euclidean setup here is the mj that we are going to do bound it above by log delta inverse mod E. We were able to do this because sigma hat was actually mod of sigma hat is less than 1. So that was playing a role here. And similar to that, like the first observation that we will be doing is that RK lambda R square comma sigma mod of this is also less than 1. And hence again, I'll be able to use Plancherel version to kind of like conclude that the pigeonhole principle is going to give you 1j. So here as well, there is not much of new techniques. It's the same old pigeonhole principle. And the highlight is only that the RK lambda R square is behaving well for high frequency, regardless of how it is behaving at every lambdas. Okay, now the challenge is high frequency. Why? If we remember the high frequency setup, like the main high frequency tool that we used to address high frequency is that the pointwise Fourier decay of sigma was used. We were able to say that it has a nice decay for all values. Now, on the other hand, here what happens is that like we are trying to address the Fourier coefficients of the sigma hat and say that is going to give you some sort of a decay. And that decay, if I'm going to plug in after a Plancherel and after the appropriate choice of delta, again, we will be able to conclude that this high frequency is also going to be smaller for us. And thereby, we will conclude that the low frequency plus middle frequency plus higher frequency altogether is going to be greater than epsilon square. Okay. So yes, so far there is, it's not challenging. So the main challenge over here is this bigger lemma, this is the technical lemma that we have. So how do we address that mod rk lambda sigma is less than or equal to mod lambda mu? Well, mu here is for me 2 times 2k plus n. I think I did not mention that in the previous slides. So how do we prove this lemma is the rest of the talk. Okay, so in a very quick gist of what is happening with the rk lambda is this slide, and then we will go dig in slowly. So we have the rk lambda as a coefficient, Fourier coefficient of the spectral decomposition of this surface measure of Coriani sphere. So what we are going to use is Legard polynomials asymptotes, and then we are going to use stationary phase method, Van der Koppel lemma at various breakages of all these rk lambdas. And since rk lambda itself is an integral, like what we are going to do is we are going to split that integral into 2 regions. One is stationary and non-stationary. And each of the phase, then we are going to address it again in sub cases, like where it is going to behave well, where we will be able to apply Legard function, where we will be able to apply Van der Koppel lemma is the rest of the story. Okay, so this is the integral representation of rk lambda. So the first and foremost reduction step is that like this is going to behave e power I lambda sine theta. It's going to behave like a 1 for us. And hence, first of all, it is good enough to consider rk lambda sigma integral representation to be of this fashion. The next fact that we are going to do is we are going to split the eigenvalues into like 1 by mu less than or equal to lambda less than or equal to 1 and lambda greater than or equal to 1. So we are going to split the eigenvalues. And with respect to the split, then we are going to deal it separately, say J1 and J2. So the first case is actually going to be like the 1 by mu less than or equal to lambda less than or equal to 1. That is going to be easily addressed via the asymptotics of Legard function. Whereas the second integral, when lambda is greater than or equal to 1, we need to exploit the phase function. Now, even here, when we are going to address the first case, the J1 and J2, the Legard polynomials asymptote will easily take care of it. And since it is too technical, I'm kind of like leaving this at it because it's just computation over here. Okay, so the second case, the phase function, what do we do? Is that because this phase function will have stationary point around pi by 2, the first and foremost step that we are going to do is divide that into 2 different regions around the stationary point and away from the stationary point. So that is going to be called as RK1 and RK double. Okay, so when we have these two things, the first and the RK1 is having too many oscillations because it is away from the stationary point, and RK2 on the other hand is going to give the base. What do I mean by that is that RK1 is going to contribute very small quantity, whereas RK2 is going to be the base that is going to give me the actual epsilon square. And both of these cases, what we are going to further do is divide according to the Legard polynomial asymptotes. So what do I mean by that? Like in the Legard polynomial, we know that like we have Bessel regime and Airy regime and exponential regime. So with respect to these regime, we have the Legard polynomial asymptotes. And with respect to these asymptotics of Legard polynomial, first in the base integral, we will be able to get the actual bounds that we are supposed to get. And finally, for the previous step, that is whenever we are addressing the oscillations part, over there we will have to repeatedly apply Van der Koppel lemma. So this Van der Koppel lemma is going to be again for each and every case, we will be dividing it as the good phase and the bad phase, and we will be keep applying the Van der Koppel lemma, and accordingly we will get the bounds. So since this is too technical, so I thought like this would be an appropriate time to, place to stop. And yeah, so I didn't realize that I'll be finishing this fast. So yeah, basically this is the treatment that we get, and it's fully computation. It's fully the oscillatory integral computations hereafter. So once we have that, the proof is done. So I'm open for questions.
So you finished your talk?
Yes,
Oh.
I had I mean, the original goal of the talk was to actually address some Falconer distance set problem on Heisenberg group setup, but it's still open, and it is the recent one that I have started off. So we have energy integrals in Heisenberg group setup as well, and hence it's kind of like very interesting to see how it is going to pan out. But yeah, unless I think I'm going to do that, I don't think I'll be presented. So this whole problem was to actually start about Falconer distance problem in Heisenberg group setup. So yeah.
Okay, so are there some questions from the audience?
Okay.
Yeah. Can you go back to the previous slide?
Yes.
So you have decomposed RK into RK1 and RK2.
Yes.
RK1 is away from the stationary point, so that has
Yes.
rapid decay, right?
Yes. Yes. That has rapid decay.
So it
yes.
is RK2 you are decomposing further.
Correct.
And so RK2 is closer to this. And yeah, can you go to the next slide, please?
So here is where the Van der Corput lemma, like we kind of like divide each and every regime into the appropriate phase functions behavior and try to address each of the cases separately.
Let's see. Yeah. Okay. Thank you.
Yes, Kalachand, you wanted to ask?
Yeah, so as you said, Ranini, that you are going to start Falconer distance problem in Heisenberg group setting.
Yes.
So are there any result so far, or
No, there is no result yet. Because the main part of most of this distance set problem was the pointwise Fourier decay in the Euclidean setup. But that being now addressed here, I think now we will be able to address many more questions. So I still haven't been able to apply this particular technique in the energy integral setup. Like we do have energy integral setup in Heisenberg group as well. But yeah, that is something which I'm planning to do with my student. So I'm pretty sure it's going to take some time.
Okay, thank you.
So are there any other questions from the audience? Okay, if there are no more okay.
I have
okay,
a question.
Yeah, ask.
So other than distance, I mean, you can also look, suppose you fix a large distance,
Yeah.
the set of directions in which you can achieve them. So say something about it, or is that study?
In Heisenberg group setup, I have no idea. Because
in the Euclidean,
in the Euclidean setup, of course, we have a lot of result. So this whole assumption on positive upper density has been, I mean, like basically even Bourgain has addressed this question for hyperplane setup. Like so in his actual paper for n greater than or equal to 2, instead of talking about like this particular distances, what he also addresses is hyperplanes, and then from there Roth's theorem actually gives the other directions, and then we look at triangles, even in the triangles, just like how you asked for directions. So this work is actually done by Evgeny Derpals and Alexei Osevich. So yes, there are many questions that have been asked in Euclidean setup, and all of these questions are still open in Heisenberg group. Yes.
Tapendu, you have a question, right?
Yeah. So Raniti, you mentioned something, the results of Alec Rice for general matrix spaces.
Yes.
I just want to asking that is there any restriction metric, like is it has to be polynomial growth or?
Oh no, this one is no, there is no polynomial growth. There is no growth actually here. It's just the double ball conditions that we have.
Which condition?
Double ball, as in like it should behave like R power the dimension.
Okay. Okay. And is any of these results like has analog in hyperbolic spaces or anything?
No,
I
so
think no, right?
no. So I mean, like Naru told that this can be extended, and with Sanjay, I'm trying to learn a few steps. Few steps for. But yeah, there are no results. I mean, like.
Okay. And how much this, like you mentioned that group action doesn't play much role here, but still,
Only for this result.
does dilation play much role in this kind of
Dilation
result?
plays, yes, dilation plays.
Okay.
As long here, even though just like left translation alone can work for the appropriate alignment. So you just have to appropriately choose the positions to ensure that it is avoiding the distances. So even if with respect to just left translation, this is going to work out well.
Okay. Thank you.
So are there any other questions from the audiences? Okay, if there are no more questions, let us unmute and thank the speaker for a nice talk.
Thank you.
Sorry, Kalachandi, may stop recording.
Yes.